Alright, you guys ready? Good morning. How is everyone? How are you holding up after the elections? So let's get started. My name is Prateek. I'm your guest lecturer for the 377 class today. And we are going to be discussing about real-world operating system design and implementation by using Linux. At any point, if you have any questions or comments, or you want to interrupt, or something's not clear, please let me know. All right. So, what's the purpose, right? Why do we want to study Linux, and what's the purpose of today's talk? So, first thing is that the hope is that you'll be able to understand real-world operating system design and some implementation concepts, which may not necessarily have been the focus of previous lectures, which focus more on abstract operating system concepts. So we are going to look at practical considerations in operating system design. And most importantly, we're going to look at Linux as our example operating system because that's the most widely used open source operating system which everyone can go and look at and study and see how it is built and how it is evolved, etc. And lastly, if you have time, we'll talk about what are the new developments in operating systems, what are the new research areas, and what's new in Linux, and how you can contribute, etc. Any questions so far? All right, so just a brief overview and a brief history. So Linux started off in 1992 as a Unix clone, right? It's right now the most popular operating system in the world. Servers, and smartphones, Android, like embedded devices like Raspberry Pis, etc. So it runs on a wide variety of hardware, although it initially started off as a desktop operating system for the x86 instruction set. And the great thing was that because Linux implements a Unix system called Layer, all the GNU programs and all the existing old Unix programs could be run on Linux without any complications. That was really a great thing. And we have all these distributions which combine the Linux kernel with some user-space software, like Ubuntu, etc., which they package everything all into one CD-ROM. And even though I'm not running Linux on this laptop for projector reasons, 2017 is going to be the Linux of the year of Linux on the laptop and the desktops. Always hoping. So just to keep things clear, traditionally, like operating systems, so when you talk about operating systems, it's like it's the operating systems, it's the libraries, etc. In the case of Linux, it's slightly different. So strictly speaking, Linux is just the Linux kernel and nothing else, right? So just this part of Linux. And if you have some user space, libraries and applications, typically those are GNU programs. So if you want to be pedantic, it can be GNU/Linux, or if you're a big Stallman supporter. Anyway, so let's, the focus of this lecture is going to be on this bottom part, focusing on the actual Linux kernel, which implements some of these operating systems functionality, like CPU scheduling, which you may have studied. So if you zoom into the kernel, right, this is how it looks like at a very high level, right? At the bottommost layer, you have the device drivers, which bridge the gap between software and hardware and implement different hardware support in order to run on a million different kinds of hardware devices. Then you have the memory management to manage virtual memory and pages, which you might have learned. Obviously, you have networking support, TCP/IP, UDP, all these protocols are implemented inside the Linux. Which have you guys taken a class on networks? All right, a few of them. All right. Then at the topmost layer, you have process management, things like fork and exec. You have the file system layer, which can make sure that you can write data to the disk. And at the very top, the user space applications, or the applications that you run, like your web browser, can interact with the kernel by using system calls. So the purpose of today's talk is to give you a very, very brief overview of each of these subsystems, right? Just, what's the major implementation highlights, what are the challenges, like what are some of the key design things which may be different from traditional operating systems, concepts taught in your textbook, etc. Right? All right. So all of that is obviously very complex, right? It's about 17 million lines of code and growing daily. It's mostly written in C, with some architecture-specific components written in assembly. Sadly, there is very limited documentation because the kernel itself is evolving so quickly over time. So, okay, I'll talk about that, but so Linux is like one of the first open source projects where anyone can submit patches and get it approved and all that. So people are constantly changing things and breaking things and all that. Even though I think the fundamental design principles remains the same. So I hope that what I cover today is going to last you long enough, right? At least the next few years. And there's a new kernel every 3 months or so, which may have some significant changes. All right. So, question for you: what's a monolithic kernel? Have you guys covered that? Monolithic, micro. Those terms make sense. All right. So, what's monolithic? Anyone? Yeah.
All the kernel functionality is written in the kernel elements in common.
Yes. So to summarize, all the kernel functionality is written in kernel mode, and essentially it's one giant program, right? And that's what Linux is. Linux is monolithic. The entire kernel, all those 17 million lines, all those subsystems, run as one program, right? So what I mean is that you take your Linux source, you compile it, at the end you get essentially one giant e.out file. Right? So that's what we mean by monolithic in this context. But remember that I said that Linux can run on a very wide range of hardware, right? You have supercomputers, laptops, different machines have different hardware configurations, etc. So how do you manage this vast complexity? And Linux does it, like every other operating system, through what are called kernel modules. Heard of those? Kernel modules? So kernel modules essentially allow you to implement functionality, right, which is separate from the kernel. You still run in kernel mode, right, but you can be at least assured that when you are building this kernel, right, when you are compiling this kernel, it doesn't have to support every device and every configuration option under the sun. Right? So at runtime, while the kernel is running, you can load and you can unload functionality by using kernel modules. So I'll go into an example of a kernel module and how do you unload and load and all of that. Right? So these pre-compiled modules, so you can write your own kernel module. Right? If you do so, you just include the necessary headers, compile another module, and you can load that into the kernel. And now you have your code running inside the kernel. So you can do all sorts of cool things, fancy things, you can break things. Like most likely that will result in your machine halting, right? And the way this is done is by a very clever way of you have specially relocatable ELF files. So you still compile normally by using GCC or something, and then you have some special flags which make it relocatable, and the kernel essentially just, so when you load a kernel, so when you load a module into the kernel, essentially what you do is just jump to a specific instruction, right? And that instruction is the start of your module, right? So it's a runtime linking system with some special changes because you want to make sure that your kernel is able to accept that module at runtime. So let's look at a few examples and let's just, to give you a flavor of what I'm talking about. Okay, this should be good enough. Any questions so far? Yes?
What do you mean by like
All right, so what I mean by loading is I'll give you an example now, but essentially, so let's say you're running Linux on your laptop or your desktop, right? That's the case. And you have purchased some new hardware, right? Like some webcam. Or not. Let's go with the webcam example, right? So you have some webcam and you plug it in. Right? Now, it's overkill to have device driver support and hardware support for all the webcams in the world in your kernel all the time. Because remember, it's one giant monolithic program. So that program size can become huge, like gigabytes of your kernel, which you don't want. You want that to remain as small as possible. So when you plug some new hardware in, the kernel searches for what's the device. So on a big table that okay, this device is supported by this kernel module, right? Finds that on disk somewhere and loads it. So that's what I mean loading at runtime. That is, you don't have to reboot. You don't have to reboot your device or your system. You don't have to restart the kernel. All of this is dynamic. Make sense? All right, so this is my Linux box. And so if you want to list what are the current dynamically loaded kernel modules on our system, the command for that is lsmod, list modules. And there we go. Whoa, whoa, whoa. Right, so you can see I have a few modules running right now. Quite a few, right? For example, right, this is the Hfs module. And for anyone using a Mac, Hfs is the file system on most Mac machines, right? So things like file systems, right? If you plug in a USB hard disk with a different file system, right? That file system support is usually in the form of some module, which you look up at runtime. Where's that functionality and load that in? All right. And you can, insert and remove modules at runtime, and the command for that is mod probe. Right, and then you just basically give your module name, right? So, well, in this case, not here, but you know the drill. All right. Any questions? All right, so let's move on to the next part, which is system calls. So, let's hear some examples of system calls. Fork, that's one. Read, can you read? All right. Let's say now open close. Any more system calls? Kill. Oh yeah. Sorry?
Yeah.
All right. There are system calls which allow user space, right, to instruct the kernel what to do, essentially. And so in Linux, these system calls, are called via some C wrapper, right, which like libc. And so I'm just going to walk through an example of what happens when you make a system call, right? Any guesses? It's on the screen. All right, so let's say you call fork, right? Because I suspect that's the system call that has received most attention in class. Right? Fork and exec and all of that. All right, so let's say you call fork, right? Now fork is implemented inside a GNU C library, right? So, some sense, if you load stdlib .h, and what's the other one? Unix standard H. Here you'll find some fork implementation, right? So it's like int fork, take the arguments, and fill it. Okay, so this is your library. Right? So, and the library does something, which we'll see what, right? To call the kernel here, which will actually do the process sorting and make sure that everything is safe and return the PID back to this library, which will return it back to the user. So we need some mechanism. We need some mechanism because remember, this is all in user space, right? So this is user space, and here is kernel space. If you make a system call, right, every system call is a transition from user space to kernel space. Clear? Now, the question is, how do you do that? You're running a program, right? C, Java, whatever, it's all in user space, and you need a safe way to tell the kernel that, hey, I need this fork functionality from you right now. So, the answer depends on which processor architecture you're running on and which operating system you have. Right? In Linux, right, the traditional way is to do this via interrupts, more specifically software interrupts. So, what you do is essentially, I'm going to raise a software interrupt. Right, so this is my software interrupt. This software interrupts whatever is running on CPU, which is your program, right, and calls an interrupt handler. This interrupt handler is the system call interrupt handler. What the kernel does, and so with this, you also pass some. You pass arguments to your system call. So you say what's your system call number, right? You want to say 4, and essentially this is like a big table. So you have system calls all numbered. So let's say 4 has number 1, 5, 7, 1, right? So if I want to call 4, I'll say my system call number is 1. And 4 doesn't take any arguments, so I don't have to pass any argument. Otherwise, you can pass arguments here. This essentially is going to be looked at in a giant system call table. Which is a table of C function pointers. Right? So every system call is essentially just a function pointer in the syscall table. So we have 4, which will be sys underscore sys 4, right, is going to point to the actual function right. So this is some kernel function, and we have these tables. You have this big table with a lot of function pointers. The sys fork, second one is sys read, etc. Right, and that will point to something else. I will point to read. Any questions? Right, so this is not as simple as it sounds. Right? There are a lot of complexities. There's a lot of ways to. So these transitions from user space to kernel space are expensive as far as time is concerned, right? It's a very expensive operation to go from user space to kernel space. You have the software interrupt has to be handled, and as you can see, there's a lot of things that go on to make a single system call. So system calls have traditionally been considered a very expensive software operation, and you should always try to reduce the number of system calls your program makes. Thankfully, Linux has a very, very optimized system call implementation, right? This used to be the case when it first started in the early 90s, but hardware manufacturers, Intel and AMD, have come up with special instructions which can make this transition very, very fast. So let's look at, so this was this abstract picture which I painted of how things work. Just to give you a brief taste of what the kernel looks like, let's take a dive into this part of the code which handles actual system calls. Questions, doubts, whatever. All right. Let's see. Okay, let's start with this, which is actually the system call table. And here's a question. How many system calls are there? Like, how many system calls do you guess would be implemented by an operating system like Linux? Yes.
367.
How did you guess that?
It was a question on homework.
Oh, really? Okay. Good answer. Yeah. Let's see the actual number, right? So, it's pretty close. And that answer changes from version to version. So remember I said every 3 months there's a new kernel. Sometimes there's a new system call, right? For functionality that new applications might need. But that's very rare. So that's very rare. Right? And other operating systems which are based on Unix like FreeBSD and Solaris are much more conservative in that sense that they stick to this core, small number of system calls and not just add a system call for small services. All right, so this is called table. This is the name, and this is essentially the function pointer. Right? This file gets read in when you compile the kernel. Right? This is some special format, and it will generate this table of function pointers automatically. Right? So, why is this? And each system call is numbered so that when you make the call, it's just an offset lookup into a table. So you have 313 contiguous ones, and a few of them which are 32-bit specific. All right. So remember I told you that this system call implementation depends on architecture-specific properties as well. So because of that, the very small, tiny amount of system call handling is implemented in assembly. So this is the assembly file which does all of that. Not expected to understand this. Just, this is where it's gonna. Right, so that's it. Right? So you copy all your arguments from the program into the kernel space, make sure they're clean, and call the interrupt handler. All right, so actually, let us see this in action, right? Let's run a program and see what system calls it's making. Let's do that. Luckily, there's a very cool utility in Linux and most Unix systems. It's called strace, which can, diagnose or instrument what system calls you're making and what are the arguments to those system calls, right? The way it runs is simply call strace and give some program name, right? It can be your program, e.out, something, whatever. Let's just run ls, right? What happens when I call ls? One would assume that, this is from the bash thing, so you need a fork, right? You need to read a lot of directory entries, so we expect a lot of reads. And it also writes to the standard output, right? It prints a message, so that's a write, presumably. So let's see whether that's what happens, right? So let's run strace ls and pipe it to less, just so that we can hear. Here it prints. So the program runs, prints the strace output, all of that. Here, you can actually see the strace output. Right? So these are system calls. Here's write. you close the file descriptor. Anyone know what this is? 1. File descriptor 1 is standard out, right? Which is basically the output of your terminal is file descriptor 1, right? So you close file descriptor 1, you close file descriptor 2, which is standard error. If you have any error messages, you write to that, you close it when your program is done, right? All right, so you can, we can go back in time, and so we were over here, we closed our file descriptors, right? We wrote a big string, which are essentially just all the file names. So we wrote this to file descriptor 1, standard out, right? So the arguments to write are which file you want to write to, the file descriptor handle of that, and the string that you want to write. And where it is. Web protect. So you can see, like a simple thing like ls can make a lot of system calls, right? It's a lot of system calls. All right. Any questions? Sweet. So let's move on to the next part, which is so we learned about strace and sort of step back a bit, right? So the next things are really device drivers and how hardware support is implemented. CPU scheduling, which I presume that you learned a lot about from a theoretical angle. So we'll see how CPU scheduling is actually done. Some memory management stuff, file systems, and lastly, locks and spin locks and all those good things. So let's start with drivers. And as I said, drivers are required because you want different hardware devices to be supported, right? And drivers are this bridge between hardware and software. They sort of encode knowledge about what the hardware exports and what the hardware functionality is, and sort of connects it to the user. So most of the kernel, a big fraction of it is actually device drivers, right? You have all these drivers for every hardware device. So have you covered drivers in class? Interrupts, drivers? All right, so I'm not going to go into too much detail as a result, but think about it this way. So essentially a driver implements a file system interface. So you have a USB device, right? That's a block device. You want to write some data to it. So that's a write operation, right? So drivers basically just export this file system interface. Okay. CPU scheduling. Another question. I'm sure you people have studied CPU scheduling algorithms. Policies, all right. I see a few nods. Let's hear some examples. First come, first serve, all right. MLFQ, multi-level feedback queue, is that correct? Yeah. Shortest job first, yes. Round robin, yeah. All right, so Linux doesn't implement any of those, obviously. What Linux does is it's called WFQ, weighted fair queuing. It's kind of similar to multi-level feedback queue, but not really. And so I'm going to be talking about some of the practical challenges in CPU scheduling. Right? So the first practical challenge is that most devices these days are multi-core and have multiple CPUs. So the main challenge is how do you design your CPU scheduler to work efficiently with multiple CPU cores? That's received enormous attention, enormous engineering effort to make sure that all of your CPU cores are best utilized. At a very high level, right? Each CPU will have its own per CPU run queue of processes, right? Each process in the CFS scene, okay, so CFS is this standard Linux scheduler. It stands for completely fair scheduler, which it isn't, but that's what it's named, right? And each process is allocated some amount of time quanta, similar to the round robin time quanta you might have studied, right? And the time quanta changes based on priority, etc. All right, so I talked about this trait of multiprocessor kind of a scenario. Let me talk about one particular challenge which exists. So let's say you have two CPUs to keep things simple. CPU 1 and then I have CPU 2. Now each process, so each CPU, right, the kernel maintains a queue essentially. So it's a list of some processes. So I have PID 1, 3, 10. Right, so this is my run queue. No. 8, 24. That's it. Right, so your per CPU run queue, right? So in some sense, so there are two possibilities here, right? One is you can treat each CPU having its own independent scheduler and run whatever CPU scheduling algorithm you want on the CPU, right? So to start with this kind of something like round robin. So processes which get assigned to CPU number 2 are scheduled in round robin fashion or weighted fair queuing fashion on the CPU. And likewise for CPU 1. It keeps it simple, you don't have to change anything. But the question is, what can go wrong? Yeah.
If you run one process before a process that needs to run as a dependency of that process you just ran, then the system will just false for the process.
What do you mean as a dependency?
So let's say I needed to do a write operation on a file, but the open operation was on CPU 1. So CPU 1 runs open, CPU 2 runs write. If CPU 2 runs write first before it opens a file, then obviously it won't be able to write the file.
Right, so you're talking about some kind of a race condition or synchronization problem. Right. That is a problem. But in this context, so remember that each process is essentially a single thread of execution. So that is a problem, and we'll get back to that very quickly. So that's one issue. So you have synchronization. So the other thing, really, is load balancing. It's possible that processes here take way too much time. Right? They're high priority, CPU intensive, and so what may happen is that some CPUs may get overloaded, right, if you have this key. So periodically, you need to sort of rebalance all your processes across all your CPUs based on how much time they have taken, how much quanta they have available, and all that. Right? And that's a very intricate and very complicated policy, right, to actually balance load across CPUs. And that's an open problem, right? That there is still not a very good solution to this, which works well in practice. There's another reason. So the trade-off is this, right? Why would you want to? So you could argue that let's just round robin a process across different CPUs all the time. So I run here, I get preempted, or my quanta expires. I run here the next time. Right? So there's no locality. I keep bouncing between CPUs. That's perfectly load balanced. Right? The drawback of that is that you suffer from lack of locality. So in this picture, we have CPUs here and PIDs here. Let's augment this and let's say, actually, Now PID. Let's read on a little bit. So you have a CPU here, CPU here. What do CPUs have? CPUs have caches, right? I mean, caches are a big component in performance, right? The other thing, so have you guys heard of NUMA, non-uniform memory access? All right, so you could imagine that each CPU, and this is true, is associated with its own main memory. So if you want to read some memory address, go to some memory bank, right? And this is your memory, your main memory, right? This cache also has its own memory. Now, it's not true. They are interconnected, but this is very slow. So if you are running, or if PID1 is running here, it accesses some memory address, right, which happens to lie, let's say, in its cache. That's very fast. That's super fast, right? If it accesses something here, so this may take 1 nanosecond. Accessing something here may take 10 nanoseconds. But if you're accessing something which belongs to another CPU, that's going to take 100 nanoseconds. So this whole tension between locality, you want to keep processes pinned on a particular CPU for as long as possible. Because all of its data resides either in the cache or over here. Right. So, that's one of the big issues. I just want to give everyone a flavor of what happens in actual CPU scheduling. All right. So the next thing is handling interrupts. Before that, let's have the question, right? What can cause an interrupt, or what is an interrupt? Yeah. Sleep.
Well, no, maybe like weeks or something.
Sleep. Okay. Yeah.
A special condition which transfers control to the operating system.
Yes. What would be those special conditions?
Like file finish reading the control that interrupt the CPU.
Right. So that's the classic example, right? So you ask your physical hard disk to read some sector off of disk. When it's done, it will transfer that to some buffer and then issue an interrupt to the CPU to say, hey, I'm done, right? And that's fundamentally it. That's basically what interrupts are, right? Now, when that interrupt arrives, what does the CPU do with it, right? Now, your CPU may be running your favorite program, right? You're running Firefox, and this interrupt arrives. Who handles the interrupt? Is it the CPU? Is it Firefox? Well, it's the operating system, right? It's the kernel which handles every interrupt. The CPU and the processor is the one which receives the interrupt from some hardware device or from software, as we have seen, right? We have seen an example of an interrupt. This is an interrupt which a user space program has raised. Right? So you have software interrupts which are raised by some conditional software, right? If you have some floating point error, that's an interrupt. So you have software interrupts and hardware interrupts. They're both detected by the processor or the hardware and they're forwarded to the kernel, right? So when an interrupt is raised, that's the term. So when an interrupt is raised, something has to handle that, right? Some piece of software inside the kernel has to handle that. And that's called the interrupt handler. And let's take another example. So this is our CPU, right? You know, so imagine some physical computer that you have built. Like, so picture some motherboard out there, right? You have a big CPU out there. You have some hardware devices which are connected to, let's say, if you have your, let's go to the disk example, right? You have your, some disk which is connected to the SCSI controller, all that. So it's like a physical connection, right? So it's like a physical layout kind of thing. So if you see the CPU, it has all these pins which connected to the motherboard. You know, some of these pins are attached to the for interrupts, so that hardware devices can raise these interrupts. And this terminology are called interrupt lines. So this is an interrupt line, and we have a lot of interrupt lines, right? For you can have a lot of hardware devices. So you have some interrupt line which connects to your disk, right? That's your disk. And when your disk is done reading the data, it will raise an interrupt. So it will say, "Hey, I'm done." So put a signal here, and whatever is running on CPU is preempted, right? You're running some assembly code, in everything assembly, right? Something's happening on the CPU, you're running a fork, the kernel is operating, it's the user space, it's idle, doesn't matter. Whatever is running gets preempted. CPU has its software instructions to save the state of whatever is running, right? You save it in a special place. But one of the first things it does after that is call the interrupt handler inside the kernel for this particular interrupt line. So whenever the kernel boots up, right, one of the first things it has to do is to say that for it's called an interrupt table. That table is the same thing. So let's assume this is interrupt line number 1, right? For line number 1, this is line and this is the function pointer. For line 1, right? What is so if the CPU is raised with this interrupt and the CPU then tells the operating system kernel that, hey, I received this interrupt, what function to run on this particular when I get this particular interrupt? So this will be something like, do IRQ with 1. It's a big function pointer table, right? And you see this pattern again and again. Right? I mean, this function pointer table is really the heart of how a lot of operating systems details are implemented. So once that's there, the interrupt can now be handled, right? So now the operating system knows, okay, I have this interrupt on this line, the disk is done, maybe I need to read the data, right? Maybe this data was read by some user program, right? So maybe somebody said read file, and the data is now ready, and that data now has to be passed all the way back to user space. All of this happens, and is triggered by the interrupt, right? That's the first thing that sets off this whole chain reaction. Right, so it's called the interrupt handler. We went over that, right? That is part of the kernel which handles interrupts. We'll go over a bit of the design of this thing. So interrupt handlers need to be very small and very compact. Right? You cannot waste any time on the interrupt handler. That's like, very, very tight C code. You can't sleep within interrupt handlers. You can't be blocked on something. And let's see, why is that, right? Why is it that interrupt handlers do right? Well, here's an example again. So, and this requires some careful thought. So you have your disk, which raises an interrupt, right, on this line number 1. Well, the CPU stops whatever it is doing, right? So there's no useful computation. So if you're doing some number crunching or whatever, that's stopped. Right? Now, because you're now handling that interrupt, right? So you're in this function, right? And you may want to read data, whatever, verify whether it's correct, blah blah blah. So the first reason that you want interrupt handlers to be very, very fast and efficient is that instead of doing work which the user wants, you're now doing work for handling this interrupt. That's first. Second, and this is where some of your synchronization and multi-threading and multiprocessing knowledge will come in handy. There's a race condition here. So interrupts in many cases can't be nested. What that means is that once you get an interrupt on a line, and once this interrupt handler function is called, the first thing this does, right? So read all that. The first thing it does is to say disable interrupts. First thing this function is going to do, right, is to disable all the interrupts on the CPU. Clear? What that does is that you may have another thing, like let's say your keyboard, right? So your keyboard operates in the exact same mechanism. You press a key, right? Some interrupt gets sent in, that interrupt has to be handled, right? Key press registered, all of that. Imagine, right? You're just sending some data. You call this thing, you disable all interrupts, right? So no matter what, how many times you press your keys, it's not going to register because the interrupt lines are blocked in the CPU when you're handling an interrupt. So because of this, interrupt handlers need to be very, very compact and very, very small. Right? The first thing you do is disable interrupts when you're handling an interrupt. Right? Because interrupt handlers cannot be preempted. So because of this, there's a split design where you get an interrupt, you disable interrupts, you do the critical work, and then you do the rest of the work later. And that's called top half and bottom half. If you're curious, that's the way the interrupt handling works in Linux. All right. Next, we'll continue our exploration of synchronization and race conditions, and what happens when multiple things need to take place at the same time. Essentially, so we saw interrupts as one way, right? You're running your program or you're running something, and well, there's some interrupt, and some other work needs to be done at that same time. So what are the other scenarios in which, okay, so why do you need synchronization, right? Why do you need locks and what's? Right, so multiple threads don't access some critical section at the same time, right? Inside the operating system, right? What are some examples of this? Like, how can such scenarios arise? So it's possible in user space, right? You have your own program, you have shared something, but what are some of the other examples in operating systems? So interrupts are one, right? Interrupts are one mechanism or one scenario where you may have this race condition, and which is why interrupts are disabled when you are handling interrupts, because that's the critical section. Can't. The other thing which you have seen is with multiple CPUs, right? In SMP systems, the kernel itself, right, is just a piece of code, right, that can run on either of these two CPUs. It can run simultaneously on both the CPUs, right? So there's a lot of synchronization within the kernel to make sure that parts of itself are protected from each other by using things like locks and semaphores, all of which I presume that you have studied. Questions about interrupts? Right. So, do you guys know what spin locks are? Spin locks. All right. So essentially, it's a form of mutex, right? Only one thing can execute at the same time, but it does this by busy waiting, right? So you keep spinning, hence the name. Uh, spin locks generally are bad. Why? Yeah, it wastes time on CPU. You are just burning CPU cycles, right? And the more efficient way of that is to sleep, right? All right. But surprisingly, inside the operating system, spin locks are extremely common, right? In general, if it's a lock, it's going to be a spin lock, right? Very rarely do you actually sleep. Very rarely do you actually use semaphores. The reason is again, right, because you know that these operations are not going to take a long time. Spin locks are much more efficient to implement and use inside these very small and very tight critical sections. So, interrupt handling, spin locks. Anything which has to do with deal with hardware, spin locks, right? So spin locks are extremely widely used. In spite of their simplicity and waste CPU cycles, blah blah blah. The other really cool and very advanced synchronization tool which is used in Linux, and this is a very rare thing among operating systems, is what is called RCU. Stands for read copy update, right? And it's a synchronization. So here's a problem, right? The problem is, let's say you have some shared data structure. It's a linked list. You have a linked list with lots of producers, consumers, all that. Have you done the producer consumer problem? See a few nods. All right. So the same thing. But so here's what happens, right? Imagine a scenario. So what you do normally is you'll have some mutex, and in the kernel some spin lock or some semaphore, and each time some thread wants to access that list, take the lock, wait for it, go through the list, find your item, and release the lock. This is expensive. As I said, spin locks are common. Semaphores are not safe in many places. So you need a mechanism such that if you have a lot of concurrent reads, right, but very few writes, you want an extremely efficient synchronization primitive which can support very fast concurrent reads, but it may have very slow writes. Right? And the common example of this is, think of caches. So if you have some software-based cache, if you're maintaining your cached items in some data structure, you would imagine that there are a lot of consumers of this data. You may have very few writes. Writes may be slow, and that's okay. But you want fast reads, right? So RCUs are a very modern, in some sense, discovery, a synchronization primitive which enable very fast reader-writer locks. And Linux was the first operating system to use them, the first operating system on which such a scheme was used, and really one of the main reasons why Linux has extremely good performance for large number of CPU systems and big SMP systems is because of RCUs and this whole new OS technique which went into it. Memory management. Any questions? So please feel free to let me know if I should spend more time on a certain area or something interests you more, like processes or whatever. Because generally this class is towards the end of the operating systems course, so you have covered all the bases. I think this time you've not done interrupts or device drivers, and so. How about memory management? Has that been covered? All right. Pages and all that, right? So I'll walk you through an example of, how some memory management is done, and that's going to be fun. All right. So if you want to look at some code, this is how it looks like. This is the diagram zoomed in, and these are all kernel functions. It's on the side, which is quite cool. And this interactive thing where you have it's a two-dimensional grid essentially. So you have functionality for let's say processing, right, at the user space interface. So that's the highest level thing. Here presumably we should see the where fork is invoked and all that. So if you zoom in here, you have syskill. That's the kill system call handler. Exec ve, this time blah blah blah, sys futex, sys vfork. Sys vfork is a function which actually handles the fork. Okay, just as an aside, which I did cover, you might have learned that forks are expensive. Is that a true statement? Like, are forks, like if I fork a process, is that an expensive operation? Yeah? How many people think forks are expensive? Show of hands. Forks are expensive. 1, 2, 3, 4, 5, 6, 7, 8. All right, 9. The rest I presume that forks are free, right? I mean, feel free to fork. Well, traditionally forks have been considered expensive because think about what goes on, right? First is the whole user space to kernel space transition. That's one. Second, you need to copy this entire process. You need to take a copy of all the memory pages of this process and create a new copy. Well, that got solved with copy on write. So you mark all those pages as copy on write. And this child process actually modifies some pages. You only copy at that time. So that was one optimization. But so associated with a process, there's a lot of data structures which are maintained by the kernel, right? Such as, the process control block, right? That's one. That's the main one, right? Each process must have a process control block. So if you are forking, the kernel at least has to create a copy of the process control block for this new child process, right? At the bare minimum. Agreed? I mean, every process should have a process control block which is unique, and it has properties of the process and PIDs and permissions and all that, blah blah blah. So at least you need to take a copy of this process control block, right? And there's a lot of state associated with the process. You have memory segments, you have permissions, you have accounting, you have how much time it's used on the CPU. So the state of a process, which the kernel actually has to keep, has traditionally been very large, and that state has to be copied, right, byte by byte each time you fork. Hence the thing, forks are expensive. Don't call me too many forks. Well, luckily, Linux has spent a lot of time optimizing the fork operation. So in fact, so one of the reasons for why threads are used, threads versus processes. Distinction? Sorry?
I mean, there are threads, there are multiple threads in one process, and those threads tend to share things like a stack.
Right, so that's user space threading, what you described, where you have user space scheduling of multiple threads within a single process. If you use Linux, if you use POSIX threads, so have you used POSIX threads in the assignment or something? Yeah, POSIX threads, right? POSIX threads are not user space threads. POSIX threads are kernel threads, right? So that's a clone operation. So you have fork operation for processes and you have a clone operation for threads, right? So the operating system creates a new thread, right, for the user. That's how POSIX threads work. In Linux, a fork operation is exactly the same as a thread clone operation, right? So the cost of creating a thread is the same as the cost of creating a process. I know, it's a big shocker. So these are some of the efficiencies and implementation optimizations which Linux has done over many years to make this possible. All right, rant over. Sorry. Right, so we looked at the fork thing. Process fork is internally it's the same code path as thread creation, right? So a fork and a clone, go through the same function basically. So in the syscall table, fork and clone point to the same function. So let's actually look at the process control block which you've studied and see what an actual PCB contains. So what should a PCB contain? Some fields. Sorry?
Any of the register
Register
values.
values. All right. That's because you want to save state to that of that process. Yeah. Yeah.
Program counter.
Program counter, register values. Yes. Excellent. Yeah.
List of open files.
List of open files. Excellent. Yeah. That's true. What was the simplest one?
Process ID.
Process ID. Thank you. Yes. Process ID, list of open files, and all the hardware state associated with that. Right. So let's go to an actual one and see if that's true. So in Linux, it's called the task underscore struct. That's the name. So as you can see, you can have you have state, which is interrupt, so unrunnable, runnable, stopped. The basic state cycle and state diagram you state for that. Pointed to the stack. The usage operation in terms of how much time it's being spent, a lot of things like that. Flags like is it on CPU? Is it actually running? Used for accounting purposes. So you might see a lot of familiar data structures, fields used here. Config preempt CPU. So remember, this is still running, right? This is one structure. It starts here as it keeps going on. A lot of fields which you talked about are actually encoded in the struct, which stores the memory information about a process. So the list of pages that's allowed to access and all those things are encoded here. Then you have task state, a list of pending signals, all sorts of things. And still, you have a lot of things like for security and credentials. So you can have access control list for a process and control what operation the process can do. And all of that has to be encoded here somehow. All right, I'm bored. Questions? Feel free. So I talked about read copy updates, which are a replacement for most read write locks. There's a lot of functionality which the kernel has to implement itself, like operations inside the kernel have to always be very careful of how they allocate memory, like internally. So for example, when you fork a process, right, you need to duplicate this task struct process control block, right? You need to take a copy of that structure and then modify the fields accordingly. Well, when you copy the structure, you need memory to copy that structure into. And remember, the kernel is the lowest layer software running. So in user space, right, if you want to copy some structure into another structure, you call malloc and then copy that over. In Java, you don't do that explicitly, although the JVM does that for you. But inside the operating system, now you need to be very careful about where your memory is coming from, where it's residing, do you have permissions, things like fragmentation, which you may have covered. So there's a lot of optimizations and infrastructure around how do you allocate memory, how do you find free memory, how do you freeInt, etc. And if you are reading the kernel source for whatever reason, you'll see a lot of references to this get 0 pages function, which essentially just finds a free page which is allocated to the kernel as part of kernel memory, gives it the right permissions, fills it with all zeros because that page may have sensitive data belonging to another application's context. Right? So this get 0 page, you see it all the time, that's like a page level allocation. And the kernel also has kmalloc, which is equivalent to malloc, but operates in a much more constrained environment. Right. So if you want to, some practical advice now. If you want to mess around with your own kernel, just feel free to download the source, and then begins the fun step of doing kernel configuration. So you can choose, you can build your own kernel to see and see which components you want. So you may want a certain file system over another. You may want to compile and support for different kind of devices, etc. The way that's done is just go to my source here. All right, so this is the very cool text-based configuration utility for the kernel, and you can specify options. So I can go to file systems. Actually, go to file systems. Here are all the file systems available for support. I can disable access to certain ones because I don't want them. Like I don't want ext3, and that will reduce the size of my kernel. Because it's all monolithic initially. Or I can compile it as a module, right? So M is a module, and that's a module which will be on my disk, but not loaded into memory all the time. That's cool. A lot of times you may want to know if you are running a program for a project or whatever, like, was my system too slow, or was my program too slow? I don't know if you have encountered this problem before. Things are not going very fast. You may expect you wrote something, you thought it was a very good implementation of a good algorithm, but things are slower than expected. And Linux has a lot of facilities to help in this regard. It has a lot of facilities which help in profiling and tracing of performance and performance events. So let's take an example, right? All right, so there's this tool called perf. Stands for performance profiler. It's a very naive generic name. Essentially what it does is gives you a top-like view of. So the right here are kernel functions, and this is the amount of CPU that I use for that particular kernel function. So you can know from user space where your operating system is spending time, and here you can see I'm spending most of my time idle. Right? This is that busy function which is raised by the CPU, which says I don't have enough work, and as a way to tell the kernel that there's no work, so that take the right action. 4.6% of time spending on tmux, which is my terminal emulator, all that. So that's really cool. That took a long time to get right in Linux, way more than 10 years to get this functionality inside. It's like one of the great things. So that's tracing. So I'm going to end with containers, unless if you want me to discuss something else. All right. How many of you have heard of Docker? Wow, that's a surprisingly large number of people. So, what is Docker? Yeah.
A way of isolating programs, and their own sort of virtual machines.
Yes. A way of isolating programs in their own virtual machines. That's very well put. What you may want to use Docker for? Why is it so popular? What are the use cases? So basically, what it enables is that you're not restricted to running one particular application on your machine, right? And you have your hardware shared by multiple users, and you protect all these applications from each other by using virtualization. Right? And Docker is a platform or tool which enables very efficient creation and management of these virtual machines. Well, so traditionally, when you hear the word virtual machine, it means a hardware virtual machine like KVM or Xen, which are completely different, right? So that's hardware level virtualization, and which is sometimes slow. Docker is revolutionary because it uses what is called as operating system virtualization. Right? So it virtualizes the operating system so that each application thinks it has its own copy of the operating system. In hardware virtualization, each virtual machine thinks that it has its own copy of the hardware. In OS virtualization, it's your own operating system. So what that essentially means is that you can have a process group, right? One process group for one application, like Chrome, which launches a lot of processes. So you can run Chrome within this container, within this Docker thing. And on another thing, you may want to run some web server inside its own container and its own thing. The cool thing about that is that, so we have all learned that process IDs need to be unique. Yes, that's the identifier of a process. Process IDs have to be unique. You can't have two processes sharing the same ID. Well, this enables that to happen. You create namespaces, so each container has, remember, it sees its own operating system. It sees its own system. So each container is going to have its own namespace for process IDs and files and memory segments and all that. So you can run. So essentially, your single machine looks like multiple machines because you're running multiple virtualized copies of the operating system. All right. So if you have more questions about this, you want to know more about Linux, I think there are a few classic books. This book by Greg KH on Linux device drivers is a great book. Two generic thing on operating systems, and all the kernel development happens in the mailing list. And as a bonus thing, you get to read Linus's rants. And that's it. If you have questions, feel free to ask me or email me. Thanks.